Okay, we're back to exponential and logarithmic applications. We should be familiar with these formulas by now. We have our growth or decay formula here. Don't forget, with this formula here, to determine the base, okay, remember that it's going to be 1 plus or minus the rate. And if it's a growth, you're going to add the rate to 1, and if it's a decay, you're going to subtract the rate from 1. The other thing to remember is that all rates need to be in decimal form. Okay? Here we have our half-life formula, where K represents how long it takes for the substance to be cut in half. And then here's our compound interest. Remember that N is how many times it's compounded in a year. And here we have compounded continuously. And that's when we use the E. So let's get right to it. Number 1. Upon graduating from college, Ashley took a job with a starting salary of $40,000. So here is our starting amount. She can expect a 6% raise in pay each year. Here we have our rate. Changing our rate to a decimal, we divide by 100. Our decimal would be 0.06. So in notes in these, so it says that after 6.959 years, Ashley would be earning $60,000 per year. Confirm this result algebraically. So they give us the result, the answer, if you will, or the ending amount. Okay? So this is going to be a growth problem. Notice it doesn't have the word compounded in here anywhere. So it wouldn't be either of these two. And it's not shrinking. It's not a decay. It's growing. She started off at 40,000 and she ended up with 60,000. So it's a growth. So we're going to be using this formula right here. Okay, and according to previous notes that were taken in this class, this was the answer. So we want to confirm if this is true or not, if this is how long it takes for Ashley to start at 40,000, get a raise of 6% each year, and end up with $60,000 in this many years. So let's plug in the numbers. So the ending amount is 60,000. The original or the initial amount is 40,000. The base, remember the little formula. It's 1 plus or minus r. Since she's getting a raise, we're growing. So the rate or the base is going to be 1 plus 0.06 raised to the t. So we want to solve this for t. So to do this, first thing we're going to do is we're going to go ahead and simplify. In the parentheses. Then we're going to undo multiplication with division. Zeros, 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 zeros. So 3 halves. Okay? So now, this is the key. When you're solving for time, you have to use logarithms. Unless, of course, you can make the basis the same, like I showed you on Thursday before spring break. Spring break. Where am I? Before Easter break. So we're going to log both sides. Then we can use the property of logarithms to bring the t down front. And then we're solving for t, so we can divide both sides by log 1.06. All right, here we go. Grabbing our calculator, turning it on, clicking OK, scratch pad. We have the log of 3/2. Now I found out you don't have to put the 10 in here, so you can just kind of, if it's 10, you can leave it blank. So 3/2 divided by and 1.06. All right, so 6.95852, which matches pretty closely to the answer they have right here. And so 7 years pretty much for Ashley to earn $60,000. All right, moving on. All right, living organisms can be dated by the amount of carbon-14 present at the time t compared to the amount present when the organism was alive. The half-life, okay, so you should have bells going off right now. As soon as you see a keyword like that, the half-life, so notice what formula we're going to be using right here. So I suggest writing it down. Okay, of carbon-14 is 5,730 years. There is your K value. It tells you that the half-life is this. So this goes in for K. So let's go ahead and start plugging in numbers as we get them. How long would it take for a 185 microgram sample of carbon-14 to decay to 24 grams. Okay, so notice this is how much we started with. That goes in the initial amount. We started off with 185. Notice that this is a decay because this is between 0 and 1. We end up with 24 grams, so that is our ending amount. It says how long? How long is t? So we're solving for t. So round the answer to the nearest 100 years. So here we are solving for t. So before we can do the logarithm here, we need to undo the multiplication. So we're going to divide both sides by 185. Okay, I'm going to go ahead and use my calculator on this one. So 24 divided by 185. Okay, we're going to change this to a decimal. Actually, what should we do here? You know what? I'm going to leave it as a fraction for now. Since I can't reduce that fraction, I'm just going to go ahead and leave it. So we end up with, I'm going to write it over here, 24 over 185 equals 1/2 to the t power. Okay, so solving for t, we're going to take the log of both sides. And if you don't mind, I'm going to bring the t down front right away instead of putting the log on and then writing a whole nother line where I bring the t down. I'm going to bring the t down front and put the log on. Now we're solving for t. Now this is multiplication, so we divide. So t is going to be approximately, these calculators turn off awfully fast. So log, it's base 10, so we don't have to put anything in there. 25 divided by 185 divided by log, and 1/2. Could put 0.5 in there. And we're going to get 2 and it says to the nearest 100 years. Nearest 100 years. 2.88753. All right, time out, time out. When I got that answer, I said, you know what? That's not correct. That's impossible. It says to the nearest 100 years, and I got 2.88753. Now, I see a couple errors in the problem. And error analysis is very important when it comes to mathematics. I wonder how many of you have been paying attention and have noticed where the errors were made. So first error, 24 grams. I'm not sure how I got 25 there. So we're going to change that to 24. Okay? Second error, t over 5730. That's what should be over here. Forgot the 5730. That should be under here, 5730. So t over 5730, okay, is equal to that number that I got, 2.887, and then my calculator goes blank on me. 53. I hope you haven't gone blank on me. Okay, now we want to solve for t, so we have to undo division. We undo division with multiplication. So we multiply both sides by 5730. And so t, now we can multiply that answer times. So 16,000, it says to the nearest 100 years. So I'm going to round that to 500. So 16,500 years. Awesome. To the nearest 100 years. Okay, let's take a look at number 3. We'll see how far we get before time runs out. We've got about 1.5 minutes left. Suppose a culture of bacteria is put in a petri dish and grows continuously. Oh, do you hear the bells ringing? Ding, 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 ding. Yeah. Continuously. Ah, gee. Which formula should we use? Yeah, this one, PERT. So let's write it down. See, we use P instead of A sub 0. P, e to the RT power. Okay. The culture doubles every 4 hours. Write a function to model the continuous growth of the bacteria. Okay, so we're going to run out of time here. So this is where I'm going to start up the next video notes right here. See you in class tomorrow.